Hi everyone. In the last videos, we talked about phase diagrams, level rule calculations, and eutectic alloys, including hypo or before eutectic and hyper-eutectic compositions, and how to calculate phase fractions in different phases of alloys. If you haven't watched them yet, please subscribe and check them out because we have more exciting videos coming up next, and they will be about the TTT diagrams, temperature transitions diagram. That's very interesting. And we will talk about the TTT diagrams for stairs and see how they affect the macrostructures of different phases of stair. And today we are diving into eutectoid and pretectic reaction, as well as hypoeutectoid and hypereutectoid alloys, and we will focus on the iron carbon systems, or FeFe3C, that is cementite, and looking at the macrostructures like ferrite, perlite, austenite, and learn how to calculate phase fractions and understand the transformations that gives the steel its properties. We will also work through a practical example problem that's very important, and to see how these calculations are applied in real estate. Okay. If you remember, in the last video, we explained eutectic reactions. Here you see eutectic, if I want to show, this dashed line is, or this point is eutectic point, okay? For a quick review, in a binary eutectic systems, binary means we have two components, and eutectic means this composition or C0% and temperatures that liquid convert to two solid phases. Okay, so in binary eutectic systems, alloys with the composition less than eutectic means if here it's 61, for example, if the composition be less than that, or C naught less than C of eutectic, are called hypoeutectic, that here show by the purple color, okay? Sorry. And solidifications begin with the primary alpha phase before the eutectic reactions, and alloys with the compositions greater than C naught. Means if C more than C naught, we call that hypereutectic, and solidification begins with the primary beta phase before the eutectic reaction. As soon as we reach the eutectic temperatures, before except alpha if we be at hypoeutectic, or beta if we hypereutectic, we have another structure or macrostructures that called the eutectic macrostructures. So these macrostructures contains the primary plus lamellar eutectic structures, or layer by layer structures. If I want to show you for the purple one here, okay. For the purple one, or here, we have primary alpha that is circular, approximately circular or grain. And you see the layer by layer or lamellar that is eutectic macrostructure. But if we be exactly at this C naught or CE, you see that the only structure that we have is lamellar or layer by layer or eutectic macrostructures. But if we or C naught more than CE, for example, we be in this region, yeah, means if C naught more than C, so it is hypoeutectic. and it is hypereutectic. What happens? Here we should have eutectic macrostructures and beta. Why? Because it's more close to beta, or primary phase here is beta phase. Okay. This review from the last video that we talk about the eutectic alloys. Okay, if you look at this phase diagram, you will notice that intermetallic compound appears as a vertical line. What is vertical line here? You see as a green color, this vertical line that I show you. Okay, this vertical line. Not as a region or area. What's the meaning of that? Means that only at 1C or composition percent, we have intermetallic compounds. So the reason is that the compositions of an intermetallic compound is fixed. It has a definite ratio between its constituent elements. For example, here you see Mg2Pb. That means unlike solid solution where the composition can vary over a range, an intermetallic compound exists only at one specific composition. For example, here is about 81, for example, yeah? For the alloy of MgPb, we see that if the composition or C be 81%, we only have Mg2Pb, okay? Exactly, we have at a steel alloy that we see cementide of or Fe3C that is fixed at atomic ratio between, for example, iron and carbon, and here Mg2Pb is the fixed atomic ratio between magnesium and lead or Pb. Okay, these compounds often have distinct crystal structures and unique mechanical or electrical properties that are they are very different from either of the, for example, pure metals. So intermetallic compounds only in vertical line when the composition weight percent is fixed. Okay. In this slide, you see the difference between eutectic, eutectoid, and pretectic. Okay, now let's review these three important reactions or invariant reaction in phase diagram. Eutectic review from the last videos, last session, we talked about that. In eutectic reaction, liquid or L, here shows by L, transforms in two solid phases simultaneously. For example, here shows as alpha and beta. For PBSN alloy at 183 centigrade temperatures and weight percent of SN 61.9 weight percent, we have the eutectic point, and these reactions occur means that the minimum melting temperatures means a little above this temperature, exactly at this composition rate, we have only liquid phase, and a little below that we have solid phases alpha and beta. Okay, something that new here is eutectoid. Okay, what is the eutectoid? In eutectoid reaction, it's similar to eutectic, but it happens entirely in the solid phases. For example, one solid phase that here shown by gamma, if cool, convert to two solid phases. For example, here we are talking about the steel phase diagram. Alpha is the ferrite. We talk about that in next slide. One solid phase in steel or iron carbon alloy. And the next one, Fe3C, that is solid phase again, and its name is cementite. So for FeC or iron carbon alloy, at 727 centigrade, and weight percent of carbon is 0.76. We have eutectoid, but one solid phase converted to two solid phases. In cooling and in heating, two solid phases convert to one solid phase. So it is the eutectoid. And finally, we have the pretectic reaction. In this case, a liquid and one solid phase. Here, S1 plus L, for example, delta plus L convert to another solid phase. That is S2, or here show, for example, as gamma. For example, delta in carbon iron phase diagram, delta is ferrite delta, the name of this phase, and delta plus L convert to other solid phase that name austenite or gamma phase. And okay, so it is another reaction, pretectic. So these three are so important: eutectic, eutectoid, and pretectic. Okay, if I want to show the pretectic usually should be in this form or in this form or something. So if you look at here, above that we have gamma plus L. So we have one liquid and one solid phase. And below that we have one solid phase. So gamma plus L convert to delta or vice versa. So it is the pretectic reactions, okay? The next one that show here by the black arrow. Okay, look at here. Above that we have lambda, and below that we have gamma plus epsilon or E. So delta convert to gamma plus E. So one solid converted to two other solids, that it is eutectic transformation. Okay. Let's look at the iron-carbon phase diagram, one of the most important diagrams in material science and metallurgy, and specifically for mechanical engineer are so important to knowing the mechanical properties, macrostructures of different phases. In next video, we see the effect of the cooling rate, the effect of the time that we keep at that temperature or something in phase transitions, and we see other phases that you cannot see in phase diagram. Only we have another phases in iron carbon alloy when we see the effect of cooling rate, because here you don't see the effect of the cooling rate. You see the temperatures, but how much temperature change by time, you cannot see that, okay? How much fast drop the temperatures or supercooling or some things, and how much time we should be at that time. So we have other phases such as bainite, martensite, tempered martensite that you don't see here, but we have in TTT diagram. Okay, in iron carbon phase diagram, that's very important in material science, mechanical engineering, relation between mechanical properties and macrostructures. It helps us understand how different macrostructures form in a cell and cast iron as temperature and carbon content change. There are two very important transformation points that you see in this phase diagram. The first one is eutectic, that is A point. If I show you this point, it is eutectic. Above that we have the liquid, and below that we have two solid phases, gamma plus Fe3C, that the name of Fe3C according intermetallic compound that you saw that in two slides, I think, before, with this vertical line, the composition weight percent fixed. Here you see that the composition weight percent of the cementite is 6.7. In some references show 6.67, but here 6.7. Okay, so here we have gamma plus cementite. Above liquid, below gamma plus cementite. It is eutectic. What about the temperatures? 1148, and the composition weight percent is 4.3. 8% carbon. So it is the eutectic, that's very important point or reaction. Another that's very important for us is eutectoid or B point here. I show different color. It's a B point or eutectoid. In eutectoid reactions or point B, if you look at the composition weight percent 0.76, okay, weight percent carbon, and about the eutectoid temperature 7 to 7. It is a tie line you see here, this 7 to 7 temperature. And above that we have gamma phase or austenite, and below that we have ferrite and cementite. Ferrite, we have two ferrite phases in iron carbon phase diagram. If you look at here, one phase you see here, it is delta, but we say ferrite delta. And we have another ferrite that we say alpha ferrite, okay? And alpha is this blue region. If I want to show here, this blue region, it is alpha phase, okay. And for the eutectic reactions, we have gamma convert to alpha plus cementite. That's very important points and reactions in iron carbon phase diagram. Okay, if you remember, I told that we have several phases for iron carbon. Some of them you can see here, some of them you should see by the effect of the cooling rate and the time or TTT diagram that we will talk about that in next video. The first one, ferrite alpha, that I show you as the blue color here. If I want to show again, it is the alpha. The property is soft, ductile, BCC or body center cubic, and iron with very little carbon. What about the range of the carbon you see in this table, okay? Between 0 up to 0.2% carbon. About the temperature, you see the range of the temperature, and you see about the structures and the property in the last column of this table. About gamma or austenite, it is in purple region. Or this region, okay? It is the gamma or austenite. If you look at the composition weight percent between 0.02 up to this corner, I mean at the end of this region, I'm talking about this point, okay? And the range of carbon 2.14 is FCC, and the range of temperature 7 to 7 up to 1493, and it can solve more carbon, and it is non-magnetic. You see other phases, for example, this vertical line that is cementite, we talk about that, delta or delta ferrite. You see the range of the composition, weight percent of the carbon, temperatures, and at the last column, you see the property. Perlite. Perlite is very important for us. Perlite, exactly, if you remember, at the eutectic point, if the composition weight percent fixed at that line here, for example, dash, so when weight percent is 4.3%, macrostructures is eutectic macrostructure. That is lamellar. Exactly at this composition weight percent or eutectoid that you see this dash line, we have lamellar. Or lamellar means that we have alpha that, for example, is the blue color, and we have the red layers that is cementite, layer by layer. This structure we say perlite. So what is perlite? Perlite exactly fixed as the composition weight percent of 0.76, okay? And below 7 to 7, from 7 to 7 up to here, we have the ferrite and cementite layers by layer. Okay. And other things, for example, gamma plus cementite you see here, alpha plus cementite you see here. We have other phases such as martensite and bainite that I told you you cannot see in phase diagram. You should see that in time temperature transition diagram that we will talk about that in next video. Okay. Same as hypereutectic and hypoeutectic and hypereutectic. Here we have hypoeutectoid and hypereutectoid. Okay. Hypoeutectoid means when the composition's weight percent of eutectic point. So means this region as the blue arrows you see here, if the C or C naught less than C of eutectoid. For iron carbon means it's less than 0.76%. We have primary phase, that is primary phase, we say peroeutectoid fry means here we have the macrostructures of eutectoid point, that the macrostructures eutectoid point, the name is pearlite, yeah? What is pearlite? Means layer by layer, means one layer. We have alpha, another layer, we have cementite. Okay, but except this layer by layer, we have some grains. That grains should include or be a alpha. But this alpha or ferrite is not pearlite alpha. It is another that is such as grain type. The name of ferrite, except ferrite that we have in pearlite, should be proeutectoid. Okay? So if I want show here, zoom here. Okay. Do you see layer by layer? Layer alpha is pearlite alpha. The red layers are pearlite cementite. But you see some grains as the blue, but not layer. These blue are named proeutectoid alpha or proeutectoid ferrite because the name of alpha is ferrite. I hope that be clear for all of you. Okay, here we see that how we find the weight fraction or something. Okay, a little above the eutectic temperature, if we want to find the weight fractions of the phases, we should have alpha plus gamma. I'm talking about this region. I'm talking about this region. So here we have alpha plus gamma. And you see the gamma as the purple austenite, and you see the alpha that's the blue color. How we find the weight fractions of each of them? Easy. From this point, we draw a tie line, intersect gamma and intersect alpha, and you need see the name of that, for example, S and R, but lowercase. Which side is far from alpha? It is S divided per total R plus S. As only we have two phases, alpha plus gamma, and the summation should be 100. So W or weight fractions of the gamma should be 1 minus W. But a little below that, a little below these temperatures, we have, I told that it should be hypoeutectoid. So I'm talking about this region, yeah? Hypoeutectoid, we have lamellar structures that the name is perlite. Perlite, you see layer by layer. The red layer are cementite, the blue layers are ferrite. But both of them ferrite of perlite, yeah? Because layer ferrite plus layer cementite name perlite. But you see some blue grain. This blue grain that I show again here, they are not perlite alpha. They are proeutectoid ferrite. Okay, so here we have perlite that is equals W gamma, and we have alpha that includes 2 alpha. 1 alpha is proeutectoid alpha or ferrite. Another alpha is perlite alpha or perlite ferrite, because alpha name is ferrite. So again, we use the lever rule and find both of them. Okay, hypereutectoid. Hypereutectoid means if the composition weight percent is more than the composition weight percent of the eutectoid. Here is the range between, so if C more than 0.76 and less than this corner or this point at 2 point somethings, 14%, we have hypereutectoid. What's the meaning? For example, here it is the austenite, yeah, we are cooling. Here we have austenite and you see some red nucleus, yeah. These red nucleus are cementite, but as soon as we reach to this temperature, and you see these, they are grain of the cementite, but these grain are not perlite. What is the name of that? It is proeutectoid cementite, yeah? Means it is primary cementite. Means before reaching to eutectoid, we have some grains that the name of this grain are cementite, but it is not related layer by layer or perlite. But as soon as we reach to below to eutectoid temperatures, we have one perlite macrostructure. Perlite means one layer blue. Ferrite, one layer blue, red cementite. But you see another grains of the cementite. This grain that bigger than here, this red one, it is proeutectoid cement. Okay, again, we can use the lever rule for finding weight fractions if the temperature above the eutectoid temperature or the temperature below that. Okay, example. We have 99 weight percent iron, 0.4 weight percent carbon steel at a temperature just below eutectoid. Determine the following. First, or A, the compositions of the cementite and ferrite, means C. B, the amount of the cementite in grams that forms in 100 grams of steel. C, the amounts of the perlite and proeutectoid ferrite alpha in 100 grams. Okay. Look at here. This composition is a dashed line, exactly less than eutectoid composition. So we are in hypoeutectoid. Okay. If I want to find the compositions, weight percent of the carbon and, for example, ferrite and cementite, we draw a horizontal line, intersect the alpha. You read the composition 0.022 and intersect the cementite, that is 6.7, okay? Next step, we are looking for weight fraction, weight of the cementite and find the amount of that. If we have 100 grams, we want to know how much related cementite. First, I should say that here we have what? We have perlite, cementite, Okay. We have perlite alpha, and we have another alpha that we say proeutectoid alpha. So how many we have? Perlite cementite, perlite alpha, and proeutectoid alpha. So we want to find all of them. The only cementite we have is perlite cementite, okay? How we can use the lever rule? Cementite is here. Which side far from the cementite is R? So R per R plus S, it should be this, yeah? If I want find as a percentage means 100%, it should be 5.7%. 5.7% of 100 gram means we have 5.7 gram cementite. In the last part, ask find the perlite and ferrite in perlite. Okay, so look at here. We are here. Again, we draw a tie line, but here intersect the eutectoid point. If I zoom in, okay, here, which side is far from the alpha is X, and which side far from perlite is V. Okay, so perlite is here. Which side far from that is V, V per V plus X. Substitute here, it should be 0.512. If we want the percent, multiply 100, should be 51.2%. What's the amount of the perlite? Amount of the perlite means 100 times this should be 51 gram we have perlite, yeah? Okay, what is the perlite? Perlite, if you remember, okay, we have the 51.2 gram perlite. We have perlite, Fe3C, perlite, alpha. The summations of both of them will reach to 512, yeah? If you remember last slide, we find the perlite cementite. How much? 5.7. So this minus this, we can find the perlite alpha or ferrite in perlite. That is 45.5 gram. Okay? And the residual should be what? Should be ferrite alpha 100. So another phase that has been left is what? It is proeutectoid alpha or ferrite. So 100 minus 51.2 should be 48 gram proeutectoid alpha. So here we have two alpha, one alpha in pretectic we have two alpha, one alpha as perlite, one alpha as proeutectoid. And we have one cementite. This cementite only is perlite. Okay. That's all for today's lesson that we talk about the eutectoid, pretectic reactions, hypo and hypereutectoid alloys, and key steel macrostructures. We talk about the ferrite, delta ferrite, alpha ferrite, perlite macrostructures that is related to macrostructures of eutectoid point. Talk about austenite. And we also went through an example problem to show how to calculate phase fraction in steel and understand the resulting macrostructures. I hope that you enjoyed this video, and please don't forget to like, comment, and subscribe to this channel, Make Talks 2025. And don't forget to turn on notifications so you will not miss the next video that will be so interesting and explore TTT diagram and how cooling rates affect the steel macrostructures. We will talk about some phases that we didn't talk about that today, such as bainite, martensite, and some things. Thanks for watching and see you in next video.